So after hearing some very detailed and very comprehensive talks this morning about, first of all, the development of the NGA models and how those models are being incorporated into sort of building code design and the national hazard maps like Mark Peterson talked about, I wanted to kick off this sort of three-talk session on sort of using these NGA models that they've been developed in more of a practical application. So how we can sort of incorporate this new knowledge that we have for the ground motion prediction equations and really apply them to specific projects. So what I'm going to be talking about today is some work that Norm Abrahamson and I did about in the last year in looking at the Bay Area rapid transit system in the greater San Francisco Bay Area region and sort of incorporating them into a new retrofit program that they were looking at. The main driving force behind this for the BART system was the fact that in 2002, and I'll talk about this in a little bit more detail, they had come up with a retrofit program which was at the time sort of the state of the practice using ground motion models, seismic source models, and came up with design spectra for different parts of their system. However, once they started getting into the structural design for the retrofit of these individual stations or sites, they soon discovered that their budget they had wouldn't allow them to basically go ahead and do the whole retrofit. So they were driven by this need to sort of prioritize which stations and which components of the entire system were more critical, and also as well sort of how much money will it take to do that. So that's sort of the driving force that they were sort of being pushed by. And then, of course, since 2002, there was this new knowledge in specifically the NGA models that they felt they could sort of take advantage of, that there was some better estimations of ground motion. There was an increase, or there was a decrease for typical strike slip earthquakes in that region, and they felt that they could take advantage of that. So for those of you that haven't been down to the San Francisco Bay Area and may not be aware of what BART is, it's our public transportation system that runs throughout most of the Bay Area. It was completed back in 1976, and if you go back originally, the original seismic design was developed in 1968. Now, since that time, there have been additional studies, and as well, there's been some extension work that's been done, some new lines that have been added. And so every time that happened, since 68 and since 76, they would go back and reevaluate the seismic design criteria, the seismic design spectra, and come up with new things. So it's evolved quite significantly since 1968, sort of along the lines of how our knowledge of ground motions and earthquakes in general has evolved over that time. It's approximately a 100-mile rail system. It consists of about 7 different line segments. Of those 100 miles, there's about 25% of the rail lines that are underground, 25% are on aerially supported structures, and about half of the system is at grade. The critical component of the entire system, of course, is the Transbay Tube, which runs from the West Oakland to the Oakland side and the East Bay, down across the San Francisco Bay over to the San Francisco site where the San Francisco stations are below grade. That's a special part of the entire system, so actually in this updated study, Norm and I didn't consider that because it has a different criticality to it all. It's about just under 4 miles long. And then as far as the stations, there's about 40 stations in the entire system, including things like maintenance yards. And about a third of those are underground. Some of them are just cut and cover, some of them a little bit deeper. There's about a third that are aerially supported stations, so station platforms. And there's about a third that are located at grade. If we now look at a map showing, let's see if I can get a pointer on. Much easier. If we look at a map showing the San Francisco Bay Area, we have the San Francisco City location here at the San Francisco Peninsula. We have, what I'm showing here in the light blue is the actual BART alignment, the system. So we've got several different lines. We have one starting down here at the San Francisco Airport in the Millbrae Station, which runs up the peninsula and into the city of San Francisco. We then have that crossing over, as I said before, in the Transbay Tube, running into the bay over to the Oakland section. We have a spur that goes up towards Richmond and Berkeley. We have another spur that comes down towards Fremont with the 2 other branches that come off of that, and that's being the Richmond, the Pittsburgh Antioch Concord line out here and the Dublin Pleasanton line. What I've also shown on this overall general map, of course, are all the significant faults in the Bay Area. So there are a couple of key ones to point out, of course, they're well familiar with. The San Andreas Fault running along here up in Marin, coming down right around Daly City and proceeding down the peninsula. And then, of course, in the East Bay, we have the very potent Hayward Fault, which runs actually quite close to a lot of the stations along the Hayward, or along the East Bay alignment. All of these faults were considered in this update as well as in the previous 2002 work. And I should point out that most of these faults, there are a couple of faults located further out here in the east, but most of these faults are strike-slip faults. So if you remember from Yusuf's presentation, ground motions from strike-slip faults typically tended to be reduced in the NGA relationships. And in one of his examples, he showed a hanging wall site where you can get higher ground motions from NGA. But if you had to sort of characterize a general sense, strike-slip motions from the NGA models would be predicting a little bit lower ground motions. To go along with this, based on the aerial distribution of the entire system, of course, you're going to get a wide range in site conditions. So you'll go from a typical NEHRP D site condition, soil site condition, to a more competent, say, NEHRP C site condition as you go throughout the entire system. So going back and looking at what was done in the 2002 study, the retrofit program, they had decided at that point to come up with two different design levels, one being the DBE, which they call it design basis earthquake, which was taken to be a combination comparable to what's done in building code maps and things, but taken to be the larger of the probabilistic hazard results or the deterministic results. And in looking at other design levels from previous extension work in the BART system, as well as other things such as Caltrans bridges in the Bay Area, they felt comfortable that they could use the 500-year design level for the uniform hazard spectrum or the median plus a half sigma for the deterministic. So for the DBE in the 2002 study, what they did is they took the maximum of those two cases. They also came up with a lower design basis earthquake level, and that was decided to be just the deterministic median MCE value from the given faults in the area for a given site location. In the 2002 study, they also developed vertical ground motions based on empirical V over H ratios applied to the horizontal motions. For this updated study that Norm and I performed, we didn't actually do any vertical motion analysis, partly because the development of the vertical NGA models are still in development stage, and so it wasn't as simple to sort of update the ground motions using the V over H ratios. And then in addition, what they also did in the 2002 study was they came up with sort of general directivity factors and also a fault normal and fault parallel component factor, which again we didn't analyze in this updated study. Looking at what was done for the 2002 study as far as ground motion models is, as I had said before, it was sort of state of practice at the time. So in terms of ground motion attenuation models, there were 5 of them that were used. It was a typical suite that we've seen before for things like the previous National Hazard Maps and other studies. It was Abrahamson and Silva, 97, the Bohr et al. Relationship of 97, the Campbell and Bezonia 2000 model, which of course was updated in 2002, but that was before or after the retrofit program was completed, the Idris 95 and the Sidi et al. 97. And one component of that was done back in the 2002 study and Yusuf's talked about that a little bit this morning, is that these previous relationships typically were defined by generic site classifications, such as Abrahamson and Silva had rock or stiff soil site classifications and a soil site classification. In the 2002 model retrofit program, they acknowledged the fact that based on these different site classifications, that wouldn't be comparable to, say, a VS 30 meters of 760, which is what they wanted to eventually come up with their reference motions for. So even though they knew that there was going to be this disconnect and there was going to be a certain amount of conservatism, they went ahead and adopted the 2002 program that, say, a rock from Abrahamson and Silva was applicable or equal to a VS30 of 760. So this can lead to conservatism on the order of, say, 15% at PGA and as large as 25% at 1 second. So another issue that BART came to us and wanted to investigate was, can we remove this conservatism and thus lower our ground motions? For the site response analysis in the 2002 model, what they did as well is they took the NEHRP site factors and they just applied those to the reference motions of the rock at 760. Looking now at another plot, what they also came up with in 2002 study is they wanted to break things up into zones. So rather than have an individual design spectrum for each of the stations or each of the sections of supported track, they wanted to try and simplify things. And so what they came up with is they started looking at individual spectra at certain station locations throughout the system and realized that a lot of them are very similar and have about the same design levels, the same ground motion levels. And so they came up with a zonation program where they classified stations and sites along the systems into 5 zones. And so what I'm showing here is the same system-wide map. I've removed some of the other faults in the area, but you can see here it's the San Andreas again for reference, the Hayward running down here, and they've broken it up into 5 zones. These zones are the first zone being those sites which are actually located along the San Andreas fault or close to the San Andreas fault. Zone 2, you have those which are sort of in the county of San Francisco, but not including those in downtown San Francisco. Zone 3 incorporates those sites in downtown San Francisco and running over to the West Oakland site. Zone 4 basically are all the sites in downtown Oakland, and as well the 2 spurs that go out beyond the Hayward Fault. And finally, Zone 5 are all those stations which are located in close proximity to the Hayward Fault. Now, within a given zone, what they did is they calculated DBE and LDBE spectra for each of the sites, and they took the envelope of all those sites within a given zone to determine sort of the zone spectrum that they wanted to use. This was allowing them to use a simplified design of having 5 zone spectra for the entire system rather than doing individual station spectra. There are a couple of things to note, however. There are some stations which, of course, would fall into 2 zones. For example, the Daly City station here falls into Zone 1 and Zone 2. And what they did is they did a comparison looking at all the spectrum in those 2 zones and decided on a point-by-point basis for those bounding points as to which spectrum to use. Now moving to sort of this updated work that Norm and I did. As I mentioned, the real driving force was to sort of come up with the new information that's available, and specifically looking at the NGA ground motion models. So what we did is we looked at the 5 NGA models to replace those in the previous 2002 study. So specifically, it's the Abrahamson and Silva, the Bohr-Atkinson, the Campbell-Bisogno, the Cho and Youngs, which represents the update to the SADI model, and the Idris. Now, the Idris model in the NGA, as you might be aware of, is only applicable for a given range in VS30 values, specifically stiffer rock-type site conditions. And so that was only used in this updated analysis for those sites which had an applicable VS30 that fell within that range. Each of these 5 models were weighted, if there were 5 or 4, if there wasn't the Idris model, were weighted equally, which is the same way it was done before in the 2002 study. And along with that, rather than use NEHRP amplification factors, the nonlinear response that's incorporated into the NGA models was incorporated directly into the hazard analysis or the deterministic analysis. And then finally, because BART wanted to prioritize those stations which were most critical and they could get most bang for their buck for the retrofit program based on their limited funds, we were directed to do this analysis for 22 site locations throughout the entire system and not bring them into zones. Although I'll show several comparisons where we make comparisons to what was previously done for the zone spectrum in 2002. Then finally, one other component of the update that was incorporated was, since the 2002 study was done, there was an update to the 2003 seismic source model for the Bay Area site region. And so that was incorporated into the probabilistic and deterministic analysis. And again, just to reiterate, we looked at 22 station locations and made the comparisons to zones, but we weren't eventually coming up with zone spectrum. So now for the rest of my time, what I was going to do is I was going to step through comparisons of the previous design spectra with these updated spectra, and then finally summarize a conclusion at the end. I'll be showing a comparison with one site within each of the 5 zones, and I'm actually going to jump around in the zones, but I'll try and explain or try and visualize and let you remember where those zones are relative to significant faults. The progression is going to go from a soft site to the stiffest site that we have with the VS of about 600 meters per second, and I'll try and point out some features of the results that we discovered in doing this analysis. So on this figure, this is actually for the Hayward Station, which is located in Zone 5, and Zone 5 are those stations which are located close to the Hayward Fault. You can see that the maximum considered earthquake for this station is a 7.25 magnitude earthquake on the Hayward Fault at a distance of roughly 1 kilometer, 0.9 kilometers. The VS30 for this site was estimated to be 270 meters per second, which of course would fall into the NEHRP D site category. And this is my only plot I'm going to show of spectra that are in a linear format. So if it's, I'll try and explain it, but I'll move to my next set of figures in log-log plots, and I hope I don't lose too many people in moving to a log-log plot. But basically what I'm going to show here to start off with is I've got 5 curves. The first 2 that are listed there in the legend is the thicker blue dashed line, and on top of that is the pink line. Those are from the 2002 study. So the blue dashed line is actually what you get for the reference rock conditions. So again, assuming the conservatism, but adopting that that's applicable to a VC boundary or a VS30 of 760 meters per second. And because this is for the DBE design level, it's a combination of the maximum of either the 500-year probabilistic hazard or the deterministic plus a half sigma median ground motion. For this case, it turns out that the probabilistic controls almost the entire spectrum from the 2002 relationship. And what you can see here is you see the expected amplification in ground motion going from a rock site condition up to NEHRP D site condition. Now, if we look at what was done as far as the update, there are 3 curves. 2 of them actually fall on top of each other. But if we look at the lowest curve in the plot, which is this thin dashed blue line, that's actually using the deterministic ground motions from the 5 NGA relationships. There are actually 4 in this case because they just wouldn't be applicable. Taking their average and plotting it for the median plus a half a sigma on the ground motion. And then on top of that, these 2 curves, which basically fall on top of each other so you can't differentiate them, that is the probabilistic and the envelope of the probabilistic and the deterministic. So although it's easy to see on this linear plots, there is a significant difference. I'm going to switch to a log-log plot on the next slide, which is the same figure of spectra. I'm now plotting things in log, such that we can see a little bit better this intermediate to high frequency period range. So just for reference, the left-hand x-axis is at 100 hertz or 0.01 seconds, going out to 10 seconds in spectral period. The y-axis goes from 0.01 g acceleration all the way up to 10 g acceleration. And again, what I have for reference is the previous 2002 spectra had a PGA of about 1 g, and the new ones based on the NGA ground motion relationships have about a 25% reduction. They have a PGA of about 0.75 g. So you can see right off the bat for this station, if you were designing something to a PGA at the DBE level, you can get about a 25% reduction in ground motions from using the procedure that was used in 2002 and updating those with the NGA. That reduction in ground motion is fairly consistent until you start to get out to the longer periods. And then actually for this case, as you get out to very long periods, there's pretty much an equal design level that you would achieve using these updated motions. If we now simplify and take off those intermediate spectra, and I just want to look at those 2 individual spectra comparing the 2002 versus the updated NGA spectra. This is again for the Hayward Station, Zone 5 DBE level. This is a simplified plot, and this is a series of plots that I'm going to be showing for all the different examples in the rest of the presentation. Again, you get about 25% reduction at PGA, about 10% reduction at 1 second, and actually you get a little bit larger ground motion as you go out to longer periods. These have now been extended out to 10 seconds, and as Yusuf said, one of the key features of the NGA models, as well as many of the features, is the fact that they now are defined out to 10 seconds. What was done before in the 2002 model retrofit program was to basically fit expected PSV and PSD spectral shapes and extend those out by form fitting or equation fitting. And so now with the NGA relationships, we have a better understanding and a little bit more robust in estimating ground motions out to these longer periods. If we do the comparison now for the lower design basis earthquake for the Hayward Station, this again, remember, would be just purely deterministic median ground motions for this site. So 7.25 magnitude earthquake at a distance of approximately 1 kilometer. You can see you get a similar type of reduction at the high frequencies, about 20 to 30%. It decreases, and then as you go up to longer periods, you actually start to see an increase over the previous 2002 results. And this is a factor of two things. One is the simplified 2002 approach in using the NEHRP amplification factors, and also the fact that As Yusef showed in his plot, the PSV, PSD actually doesn't really start to curve over as quickly as we thought prior to sort of the NGA relationships. Now if we move to Zone 3, which is the zone that starts in the East Bay at West Oakland and goes across to the sites in downtown San Francisco, again, we have a similar site condition. We have a VS30 of about 270 meters per second. The controlling earthquake for this site is again the Hayward Fault, but we're at a little bit further distance away, so we're at 7.6 kilometers. And you can see in this situation for Zone 3, the comparison between the red dash curve and the blue curve is a little bit closer at PGA, on the order of maybe about 10%. It's pretty consistent, and then as you get out to the very long periods, about 7 or 8 seconds, so some of you get about the same design levels. If we then look at the lower design basis earthquakes, so just remembering again that this is purely deterministic median ground motions, you get the same type of results. You get a reduction of high to intermediate frequency ranges, and as you get out to the finally very long periods, you get about the same design levels, or you get a little bit larger for the NGA in this case. If we now move to a station which is located closest to the San Andreas Fault, this is the station Daly City, which is located in Zone 1. And I should also point out that in the 2002 program, the Daly City spectra was the one that controlled all the spectra in Zone 1. So this is somewhat of a similar comparison in that sense. The MCE for the San Andreas Fault was taken as a magnitude 8. The distance was 2.9 kilometers. And the NEHRP, as I said, the VS30 for this is 460 meters per second. So I'm plotting again, log, the comparison between the Zone 1 spectrum for our NEHRP C site classification and this updated envelope NGA relationship-based spectrum. Again, you see a similar type of reduction at the high frequency at PGA and also over intermediate period ranges. And then as you get out to the longer period, you start to see, in this case, an increase of the motions relative to the previous 2002 study. The other thing to note that's a feature of the NGA models that wasn't as evident in looking at the pre-NGA models is that there is a real shift in the spectral peak as far as a period as you go from both magnitudes in different magnitudes and as well in different site categories. So as you go to a stiffer site classification, this peak in the spectrum actually starts moving to higher frequency or lower periods. That wasn't as evident in the previous one, so as you can see our comparisons, the location of the peak between these two cases, there is a difference, and as I'll show in the last case, which is the stiffest profile I'll show, there is a big shift. Looking at the deterministic, the lower design basis earthquake level, you get again the similar type of results where you get a reduction of about 20 to 30% at PGA and intermediate frequencies. And then as you get up to longer periods, you start to see an increase of the NGA relative to the pre-NGA results. Moving now to Zone 2, which is the intermediate between those sites located close to the San Andreas and those in downtown San Francisco. We're now looking at the Glen Park Station, which is actually an underground station. It has a VS30 of about 490 meters per second, so again, we're moving to a little bit stiffer site. The controlling event for this station is again the San Andreas, so a magnitude 8, but a little bit further away at magnitude or a distance of 7.7 kilometers. And I'll cut to the chase on this one. It turned out that based on these updated ground motion numbers, that this site actually is no longer in need of retrofit, whereas if they use the 2002 studies, those results, then they would have to go in and actually do a retrofit. So this is one of those sites where BART was able to reevaluate it using new information and determine that it didn't need to be retrofitted or put into the retrofit program in that sense. The other thing to note then again, as I had mentioned before, is the peak of the spectral shape is moving to a shorter period. We get similar results for the deterministic. Seems like these are pretty repetitive. If we had to generalize, there was basically a reduction at the high to intermediate frequencies, and at the longer periods, they're about the same, if not a little bit larger for the NGA models. Then finally, looking at the last site, this is Zone 4. And Zone 4 were those sites located in the East Bay that were typically not close to the Hayward Fault. And if you remember, there was one splay that went off sort of a northeasterly direction that goes out to Pittsburgh and Antioch. And there was also one that goes out to Pleasanton and towards Livermore. So as you get away from the Hayward Fault, you know, there are other faults in the Bay Area which are controlling the MCE. So for example, for this site, which is the Walnut Creek Station, the controlling earthquake is magnitude 7 located on the Calaveras Fault, which is at a distance of about 6 kilometers. It has a VS30 of about 600 meters per second that was used in the analysis. And as you can see, as I mentioned several times before, the shift in the peak spectrum as you went to the stiffer sites. So now this is peaking at around 0.15 seconds. And so it's moving it back to a higher frequency based on the VS30 as you would expect from site response analysis. The thing to note about this station is that you're seeing now a reduction over all frequencies or all spectral periods. And as you get up the longer periods, you're actually seeing quite a substantial amount of reduction. If we next look at the deterministic, the LDVE design level for this case, you can see you're getting about a 50% reduction over the entire spectral period range. And so this is another example. They still need to do a retrofit for this station, but they're able to go in and say, okay, we have this new information. Let's see if we can take advantage of it and come up with a better estimate of ground motions for the retrofit program. So in going through the 22 stations that Norm and I looked at, some of the conclusions that BART came to is that they were able to reduce the retrofit demands for the aerial guideways, the aerial stations, and the underground stations. And in particular, for the underground stations, they were able to remove any need for retrofit for 3 stations, the Glen Park stations that I mentioned, the 12th Street station, and the 19th Street station, which are both located in downtown Oakland. And in general, BART is able to realize a savings of about $800,000 in their retrofit program from the 2002 study using these new NGA results. Thank you.